Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of the absolute and relative complement as well as the Cartesian product of sets, which allowed us to construct ordered pairs out of unordered sets of data. And in this video what I'm going to do is I'm going to try and give you a kind of big picture idea of the setup that we have in mathematics in order to start proving things. So when we talk about mathematics, I want to come up with this term of a mathematical structure which has this idea of kind of objects and relations between those objects. But before I do that, I want to give kind of a very kind of relaxed overview of some of the different types of propositions that you'll see arise throughout the notes. And you've probably already seen these before, but just to give you a rough idea of what names we use for different types of propositions in maths and why we use those. But really take this table kind of with a pinch of salt. It's not a rigorous definition like the previous definitions that we've been introducing. So the first one to start off with is the most obvious one, that we have a theorem. And generally we just say that a theorem is an important proposition. So something that's an important statement that we have in maths, we kind of promote it to the word theorem. The other word that you might see floating around is the word lemma. So again, all of these, just to reiterate, are propositions on the left. They're just different kind of grades of propositions that we kind of rank them in maths. Now a lemma is just simply a shorter proposition that is normally used to prove a theorem. So you might have a really kind of complicated theorem that requires a really long proof, and in order to prove it, you kind of prove maybe say 4 lemmas beforehand, and then in the proof of the theorem you can say, oh, by the previous 4 lemmas it follows that the theorem holds. That's kind of the thing that I'm referring to here. And the last one we're going to look at is just a corollary. And a corollary is just a word to normally say that that's a kind of statement in which the proof immediately follows from a previous theorem. So we say here it's a proposition or statement that follows immediately from a theorem. And in the table in the notes I also talked about a conjecture, which is basically a proposition or theorem that is yet to be proven. But we're not really going to go into that. That's not too important in this course, because you're not going to come across really any conjectures, because generally anything that's been promoted to the status of a conjecture tends to be very, very difficult to prove, and normally you would become very, very famous if you manage to prove that thing. So that's not something we're going to address in this course. And I kind of briefly outlined at the beginning that one of the things that I wanted to talk about was this idea that I've kind of constructed of a mathematical structure where we have kind of objects, which are kind of the elements of our sets, and then we have relationships between those objects. So that would kind of be like, say, I don't know, that we could take the natural numbers as our objects and addition as our relation. And it's really, proofs are kind of normally constructed on this idea of mathematical structures. And what I want to do is I want to start off with this quote here that I think is particularly appropriate to talk about mathematics, which is by Poincaré, which says, mathematicians do not study objects, but relations between the objects. Thus they are free to replace some objects by others, so long as the relations remain unchanged. Content to them is irrelevant. They are only interested in form only. So what are we saying here? Basically what Poincaré is saying, that when I talked about this kind of idea that I'm constructing of a mathematical structure, it's not the objects that are important. It's not the elements of the sets that are important, but it's the relationships between the elements of the sets and the conditions that we put on those relationships that are important. And this is very crucial in mathematics, that when we talk about kind of abstractifying things, we realize the specific examples or the specific sets that we look over are not so much the important things, it's just the general structure that we look at. And that kind of ties us into when we're looking at things like linear algebra, where we're going to be specifically discussing a particular type of structure on sets. The sets themselves or the specific sets are not so important, although we will look at some examples of specific sets with structure on. So again, I've got a definition here, but really take it as kind of a loose one. So I've written here as a mathematical structure, I want to say, is a collection of objects, which are like elements of the sets, together with some defined relations between those objects, along with a collection of propositions about the relations which are assumed to be true. So that is, we start with, say, with some set, which are, and the elements of that set are the objects, and then we define some relations, or some relationships between those objects, a bit like I said, addition and natural numbers. That would be an example of relationships. And then with those relationships, we collect together a series of propositions which we assume to be true about those relations between those objects. And we refer to those propositions as the axioms. So the collection of true propositions are called the axioms. That's our axioms of our mathematical structure. Those are the things that are assumed to be true. The word axioms follows from the word axiomatic to mean self-evident. These things are self-evidently true. And that's a kind of start, or the kind of framework that we start proving things in anything in mathematics. So if we're discussing something like linear algebra, we'll start with a set, we'll start with some relations between the elements of that set, and then we'll have some axioms about those relations. And then from that setup, we then start proving things in maths. So it's important here that then we say we have a statement about something in that mathematical structure. We prove it only using the axioms that we've been given. Those are the only things we can assume to be true. And then once we've proven the truth of that proposition or theorem or whatever it might be, then we can use the truth of that theorem to prove subsequent theorems. So it's kind of, we keep constructing a larger and larger framework, or a larger and larger kind of subject in linear algebra. We have more and more theorems, and they're kind of built on previous proofs of other theorems and propositions. And that's kind of what we're going to do. That's really the whole point of mathematics. You start with these initial things, these axioms, the sets, the relationships between them, and from them you build this entire structure. You build all these proofs from all these initial conditions. So what's a kind of example? Well, I gave you already a brief example of a mathematical structure, something like the natural numbers with addition, but I want to take here the integers as our objects, with the relations on Z defined as the usual addition, usual multiplication, and the usual ordering. So what I mean by that is we have the usual addition, 1 plus 1 is 2, and so on. 1 times 2 is 2, and various others, right, for the multiplication. And the usual ordering just means that we have that 2 is greater than 1, or minus 1 is less than 3, things like this. We have the usual ordering on those numbers. So that's our example here, where Z are the objects, and or the elements of Z are the objects. And the relations are this addition, multiplication, and the ordering. So now normally we would write down some axioms, but in this situation we're just going to say that these things are necessarily true, these particular statements, because of the definitions that we would have given about addition, multiplication, and the ordering on Z. So I'm not going to write all of these out. You can look at all of them in the notes. But here's just a portion of them. So these relations satisfy the following propositions. And I write, so let's look at this first one here. So using our first order logic, understanding now, this is saying for every x and for every y in the domain of discourse, which in this case is going to be the integers, x plus y is in Z and x times y is in Z. So in other words, this is just a property known as closure. It's saying that if I take any two integers and add them together under our usual definition of addition, then that necessarily the sum of those integers is also an integer. And simultaneously, if I take two integers and multiply them together under the usual definition, that is also an integer. Now, so that is a true statement. Another one here could be something like we have here that for every x in the domain of discourse, x plus 0 equals x. So there's this special number that when I add it to any other number, it basically doesn't change the original number. So that's kind of an additive identity is sometimes what it's referred to, but we're not going to worry about that too much. So we've got x plus 0 equals x, and we also have a kind of multiplicative identity, which is 1 in this particular case. That is that when we multiply our elements by this special number, which in this case is 1, it doesn't change the number again. So this is capturing an interesting structure about identities on that space. We have another one here which says for every x, every y, and every z, that it satisfies this property that x times y plus z is equal to x times y plus x times z. So this is like an axiom or proposition that's saying something about the kind of mixing of the two relations, that if I have a times and a plus. And in other words, what this is called is the distributive property. So it distributes across the two values. And the final one I'm going to look at is simply just that if for every x and every y, x plus y is equal to y plus x, and x times y is equal to y times x. So in other words, it's just saying that under this definition of addition and multiplication, that the addition and multiplication is what is known as commutative. That is, the order in which I do those operations doesn't matter. So what was our setup here? Just to reiterate again, we had our objects, which were the elements of Z. We've had these relations we defined on them as addition, multiplication, and the ordering. And from those definitions, these various statements were necessarily true. Now, how would I try and construct this if I was doing it kind of in an axiomatic way? Well, you see, again, it wasn't so important what what the set was, what the objects were, I could change this now, right? I could remove Z, make it any set, and then just say define addition, or define an operation that I call addition, multiplication, and ordering. And I'm not going to actually specifically say what that is now because I don't know what the actual elements are of my set. But I am going to say that I want to have an addition, multiplication, and ordering such that they satisfy these conditions here, where I replace Z now, or my domain of discourse, with just a general set. And that's kind of how we start doing maths, because we don't care about the actual objects themselves as much. Those are not so important. It's just the structure that or the relations and the axioms that we have on those relations. And where this is kind of appropriate is, let's look at this theorem here that's going to be particularly useful for constructing proof by induction. So this is a particular theorem about the integers. So if we have S is a non-empty set of integers with the property that there is an integer n such that n is less than or equal to m for all m in S. So then we say that S should have a least member. And this is going to be particularly important, as I say, for constructing proof by inductions. And we're specifically here saying that this is something special about the integers, right? Because we're saying it's a non-empty set of integers. So how do we prove this? Well, let's write our proof out here. The first thing that we want to do is, as S is non-empty, it follows that it contains an element, and we'll call that element X, right? Because our initial statement says that S is a non-empty set of integers. Now, let's construct a new set, T, and that set T is going to be constructed in the following way. It's the set of elements running from N, that is the kind of this lower bound of S, all the way up to X, and we just kind of run along. Each successive step is just adding on one because we're only looking at in the set of integers in this case. Now, as T has finitely many elements, it follows that the intersection has finitely many elements. Well, that follows immediately by just thinking about intersections, right? If I have one of the sets in my intersection that has finitely many elements in it, then it must be that the intersection must have finitely many elements. That you can't have it that it has infinitely many elements. The intersection cannot have infinitely many elements if one of the sets has finitely many elements. And that's fairly obvious just by thinking about it by drawing a picture. So, as well, since X is in S and X is in T, it follows that the intersection of T and S is non-empty, right? Because the intersection is the set of elements that are common in both, and because we know that X is common in both, X is both in S and T, it follows that T intersect S is non-empty, and it's important that we understand that this set is non-empty. Now, since this set is non-empty, and it is finite, or it has finitely many elements, it must have a least element, because if I have a set, and I've got this ordering defined on it now, right? I have an ordering defined on my integers, as I did before. It contains now finitely many elements, so I can arrange that in an ordered way, and therefore there must be an element in there which is the least element. Hence, it follows that S has a least element, or a least member, right? Because if the intersection has a least element, then S must also have a least member, because it must overlap with S. And that's it. That's the end of our proof. So that shows us that for any non-empty set of integers with the property that it has some kind of lower bound on it, then it must be that set has a least member. Now, okay, as I said, this thing's particularly important for discussing proof by induction, which we'll get onto next week. But even more so, let's go to our idea of this thing about mathematical structure. Does a well-ordering principle, does this theorem hold for anything else? Well, we realize here that it had nothing to do in the story with the integers. The only thing that relied, or that this proof relied upon, is it relied upon the fact that we had the structure of the integers, like we had effectively those conditions that we wrote down, those propositions, but I could have written down those conditions regardless of whether or not the set was the integers or not. And I also needed to have this idea of addition and multiplication and ordering. So this kind of ties back to that quote again by Poincaré, where it's saying that it's not the kind of objects that are of interest to us in maths. It's not that this theorem holds only specially for integers. It holds for any set that has those relations on, and those relations satisfy those system of axioms. So this is really what we want to kind of think about our big picture of maths. So I'll go back to the kind of big camera here. That really when we start our subject, we start with some objects, we then put some relations on those objects, axioms about those relations, and then we start to prove things. And those general statements then hold for any particular set that I put in. If I want to put the integers in, I might want to put the reals in, whatever it might be, but the setup is generally the same in maths, and it's really, to reiterate here, it's the whole mathematical structure that is important, not the underlying sets individually. So that's where we're going to conclude this video. And next week, we're going to really move on to this idea now of let's actually prove some specific things in maths and see if we can kind of break up into kind of different categories of proofs. In other words, things like direct proofs, indirect proofs, proofs by induction, proofs by contradiction, by contrapositive, and all these things tied together now with the stuff we've done before, because we're going to need our idea of sets, because those are going to be the things that are our objects in the story. We then want these relations. We have logic from which we can construct the proofs, and we construct those proofs from these series of true propositions, or these axiomatic propositions that we assume to be true, which we call the axioms of our theory. So we start with them, and then we are able to prove things through these various different proof techniques that we've got, as well as realizing equivalences between different propositions that we've already constructed in our propositional logic section. So once again, I reiterate that you should read the notes on the Moodle page after this, as well as trying any of the problems that relate to this video in the module handbook. So thanks very much, and see you next week.